Welcome to lesson 9-7. We're factoring perfect square trinomials and we're also factoring the difference of two squares. Let's think back to some of our special cases that we had when we were foiling. We're multiplying binomials times binomials. Okay, think about the patterns that we saw. We saw a perfect square obviously in the first term and in the second term. Hopefully the square root of that last term times 2 gives us our middle term. If it does, we know we've got a perfect square, as in this case here. Let's check the second one. Perfect square here, perfect square here. But the square root of 9 is 3. 3 times 2 is not 10, it is 6. Let's look here. We do have another perfect square, but the square root of 36 is 6 times 2 is 12. So we can see here, here's the perfect square, here is one that is not. So recognizing those perfect squares are going to be helpful to us. And anytime you have a perfect square, I would ask that you write it in the form a plus b squared or a minus b squared. And remember, when we talked about perfect squares, the a times b, we get doubled inside here. Okay, notice that the same is true with adding or subtracting. Now, one thing that you should recognize instantly is if you don't have a b value in your initial trinomial, okay, then you know it's going to be the difference of two squares, and it's going to be in the form a minus b times a plus b. So you can factor a perfect square trinomial into a binomial squared. That's the kind of the key with some of these special cases. Let's see some examples of what we're talking about here. Oh, maybe not. All right, let's look at the first example here. I'm hoping I didn't lose a page somewhere. But notice how we've got 16 as a perfect square, and the square root of 16 is 4. Is 8 double of 4? Yes, it is. So we can see here how this perfect square is x plus 4 quantity squared. Notice in our second example, we've got a perfect square of 64 again, and notice how we've got our first term, which is also a square. So I'm thinking the square root of 64 is 8, and 8 times 2, you guessed it, is 16. So we've got n plus 8 quantity squared. And then in our last one, we've got 64 again, and notice our b value is minus 16. So it's going to be the same as the first example, except we have subtraction going on. Now, let's look at when we don't have an x squared, we have an a value here. Now notice this first term is still a perfect square. It's 16h squared. 16 is a perfect square, and so is h squared, and then 25. So if you think about, and you can kind of unfoil, if I had 4h right here, and then I had factored out a 4h here, my signs are going to both be positive based on these two signs, here and here, and the square root of 25 is 5. Now, having written this out, I can check my outers, okay, my inners, so my outers and my inners both give me 20h. 20 plus 20 is 40. So this is 4h plus 5 quantity squared. Go ahead and see if you can figure out the other special cases below. When you're ready, check your work. Three g minus 2 quantity squared, 2t plus 9 quantity squared, and 2t minus 9 quantity squared. Now, a bell should be ringing as soon as you see this question here and ask yourself, what has happened? My outers and inners have canceled out. So instantly, you know that hopefully your C value here is a perfect square, which it is, which tells us that we're going to have 4 for our last term in each binomial, and then a or x in our first term, and that one is going to be the opposite of the other. So there's our difference of two squares, factored completely. Go ahead and try the next couple examples. And again, notice how your b value is not here. It is canceled out because our outers and inners have done that for us. Now, with something like example 4 here, we still have two squares, right? And it's the difference of two squares. So we still have that, but now we have to think about the fact that we don't just have an m for both terms, but we have a 3b for both of these terms. And then one is going to be minus 5, and then the other is going to be plus 5. And again, you've got to think about your outers and inners as you move forward. Okay? Go ahead and try the quick checks. And we're left with 3v minus 2 times 3v plus 2, 5x minus 8 times 5x plus 8, 2w minus 7 times 2w plus 7. Okay. Now here, notice 5 is not a perfect square, but we know our outers and inners have canceled out. But think back to the last example from yesterday's video, in that we could factor out a greatest common factor. In this case, if I factor out a 5, I'm left with x squared minus 16. Guess what? Both of those are perfect squares, right? So then I can factor that into, and again, the 5 still stays out here as a factor, okay? But I've got x minus 5, or x minus 4, I'm sorry, times x plus 4. Go ahead and try factoring the next 3 problems out. Don't forget to look for a greatest common factor before you do so. Here we factored out a 2, and we're left with 2y minus 5 times 2y plus 5. In B, we factored out a 3, and we're left with c minus 5 times c plus 5. And in C, we factored out a 7 to be left with 7 times 2k minus 1 times 2k plus 1. That was just a quick review of some special cases. If you have any questions, please email me or bring them up in class tomorrow. Thank you.